we have looked at the practical, or like the half-life, and how to calculate it, what might be involved. We looked at a bunch of different demonstrations. Do your notes? Now we're going to kind of look at some of the more practical uses, like how half-life is actually useful, not just how to calculate it anymore. And so we actually, and this says uses for radioactivity, number 1, and we actually talked about this last year with carbon dating, when we were looking at radiometric dating. But carbon-14 is an isotope of carbon, and it's able to find the age of once living things. So if it's just of a rock, you can't use carbon dating because a rock was never once living. So anything that is decayed or fossil remains, obviously those are coming from once living organisms. So when animals eat plants, they take in carbon-14. It's just a natural isotope. Well, once an animal dies, they quit eating. So they quit taking in that carbon-14. And so over time, carbon-14 is going to decay into nitrogen-14. So it's going to change and go from having 6 protons to actually having 7. Okay. And so the half-life of carbon-14 is 5,730 years. That's its cycle. So every 5,730 years, another half of that sample will decay, right? And so all along, we've been taking a sample amount and cutting it in half. And so the time it takes for that to happen for carbon-14 is 5,730 years. And so within a living organism, the level of carbon-14 remains constant because, let's face it, if they're living, they're going to have to constantly be eating, and so they keep replenishing that amount. But once the organism dies, the amount of carbon-14 decreases at a regular rate, like clockwork. Okay, and so we're going to take a look at this brain pop. It's going to kind of show and talk about this. Because carbon dating is a very useful, very popular, very wide used method because, let's face it, we're looking at a lot of things that are living. Right? We're trying to learn more about them or how old they are. I'm going to start with this.
What do you think? Let me see. Oh, that's Elon. I buried it here in the yard 2 years ago. Yeah, why don't you put it back? Dear Tim and Moby, how do scientists use carbon to date old fossils and stuff? From Stripe and Beetle Dogs. Scientists have lots of different ways to date fossils and artifacts. One of the most popular methods is carbon dating, or carbon-14 dating. Carbon-14 is a radioactive isotope of carbon. Isotopes are 2 atoms of the same element with different numbers of neutrons. The most common isotope of carbon is carbon-12 with 6 neutrons and 6 protons. Carbon-14 has 8 neutrons, and it's radioactive. It's nothing to be afraid of. Radiation occurs naturally. About 1 in every trillion carbon atoms is a radioactive carbon-14 atom. That includes the carbon inside the bodies of all living things. Carbon dating compares the amount of carbon-14 from, say, an old bone to the amount that's in a similar substance today. Well, radioactive substances are unstable. That means they decay into different substances over time. When a carbon-14 atom decays, it gains 1 proton, becoming a stable nitrogen atom. In a group of carbon-14 atoms, like the ones in your body, half of them will go through this radioactive decay every 5,700 years. If you wait another 5,700 years, half of the remaining carbon-14 atoms will have decayed, and so on. The amount of time it takes for half of a radioactive substance to decay is called its half-life. So carbon-14 has a half-life of 5,700 years. When a plant or animal is alive, the amount of carbon-14 in its system doesn't change. Well, Yes, the carbon-14 in our living bodies is slowly changing into nitrogen. But we're also constantly taking in new carbon-14 atoms when we eat and breathe. Once a creature dies, though, it stops eating and breathing, so it doesn't take in any more carbon-14. From that point on, the amount in its body decreases at a steady rate, with half of it disappearing every 5,700 years. Scientists who study a life form's remains can tell when it died by comparing the amount of carbon-14 that would have been in a living creature to the amount that's left. Carbon-14 dating can only be used on the remains of living things, and it's only accurate to about 60,000 years ago. Other radioactive isotopes can measure much older things, including non-living substances like rocks. Using radioactive isotopes to date objects is called radiometric dating. Well, uranium-238 has a half-life of 4.5 billion years, so it can measure things that are as old as our planet. I don't think that's from our planet.
Good guess. Okay, so uranium dating, just like they ended with, is used to determine the age of rocks. One of the ways.
Some rocks contain uranium, which have two radioisotopes with really long half-lives. Just like they said, uranium-238 is billions of years. And so the amount of uranium and their daughter nuclei are measured, and then the age of the rock can be calculated. And again, daughter meaning like a derivative, or it's coming from the original uranium isotope. Okay, so it's the same process as with carbon dating. Basically, it's just obviously for things that are much older. So there are limitations. You know, if something isn't even 5,730 years old, you couldn't use carbon dating because it wouldn't have even gone through a single half-life yet. So there are restrictions where not every isotope is beneficial for every situation. So, you know, it's not a foolproof method, but it is a good way. Same thing with uranium. If the half-life is too long and the item's too young, then it's not going to work. Do you need me or somebody else?
I was just going to
Are you?
I could get my work if we're doing
We're doing just notes, so you can just watch them on Google Classroom. Thank you. Are you doing the leadership thing?
Yeah.
Okay, cool. All right, good luck, have fun. Okay, so the second use of radioactivity is for treating cancer and radioactivity, or through radiation. And so if we take a look, obviously we know that cancer occurs when groups of cells kind of go rogue. They start growing out of control. We're actually going to talk about this a little bit more later. But what we're just going to focus on right now are some of these kind of practical uses of this radiation. Because again, I said radiation gets a bad rap. It's like, oh my gosh, it's dangerous. This is going to kill everybody. Well, actually, it can have some really, really good medical benefits and heal and help people. Okay, so radiation given off during nuclear decay can stun the growth of a tumor. It basically kills any cells that it is directed at, which is why it has to be so precise, so pinpointed, because you want to just attack the cancer cells, but if it hits any of the healthy cells, it's also going to kill them as well, which is why there are some side effects of radiation. If you know anybody who has ever had to go through radiation, you know, there are some side effects. The medical profession feels like it's the good is outweighing the bad, and it's so specific and focused that the healthy cells are minimized that get affected. Like they try to make sure that they don't affect as many as, like, we're trying not to affect as many as possible, and just go after the cancer cells. So the radiation is not discriminatory. It'll kill anything that it is pointed at, basically. Okay, and so this one is going to kind of explain this.
You know, I promised Rita I'd take care of Pickle while she's away, so you can't run around shooting lasers at him. And you can't do whatever that was either. Dear Tim and Moby, I was watching a hospital TV show and they put a woman into a scary looking white tube. What's up with that? Sincerely, Nikki. Well, what you probably saw was a body scan. Body scans are used to look inside your body to see if there's anything wrong with you. If there is something wrong, doctors can often pinpoint exactly where and what it is by examining the images produced by the scan. I thought I told you not to do that. There are two major types of body scans. The first type is called a CT scan. CT stands for computed tomography. A CT scanner looks like a big square donut. A person is slid into the donut's hole, and the machine rotates all around them, shooting out X-rays. As the frame rotates the full 360 degrees, a detector records hundreds of images from all angles. These are fed to a computer, which combines the images to create a picture that's like a cross-section or a slice of a patient's body. The newest, most advanced CT scanners can even produce 3D models of your insides. No, I said they're like slices. CT scans give doctors a detailed view of just about any part of a patient's body without having to cut anyone open. They're one of the key tools doctors use to detect the presence of cancer. If a patient has been in a car accident or other trauma, doctors will often order a CT scan to see if there are any internal injuries. Anyway, another type of full body scan is called magnetic resonance imaging, or MRI. There are no X-rays in an MRI. Instead, the patient is slid into a long tube that acts like a giant magnet. Inside an MRI tube, you have to lie very still for a while as radio waves are sent into your body. These waves, along with the magnetic field, cause the hydrogen atoms inside your body to emit weak radio signals of their own. Those signals are measured by a computer and used to create a series of images. Unlike CT scans, MRI scans don't make good images of bone, but they can make much better images of soft tissues than CT scans. Since organs like the brain, heart, lungs, and liver are made of soft tissue, MRI scans can be very useful. And MRI scans can make images from any angle, front to back, top down, side to side, or anything in between. Well, recently doctors have also been using a new type of body scan called a positron emission tomography scan, or a PET scan for short. PET scans measure the biochemical activity of your body's cells. In a PET scan, a patient is given a small dose of a radioactive chemical. Cells that are particularly active take in more of this chemical. The chemical gives off signals from inside the body, which are measured by a sensor. Since cancer cells tend to be very active, they tend to create the most signals, so PET scans can pinpoint where tumors are. They can also help determine what stage of cancer a person is in, and even whether a tumor is cancerous at all. Wait a minute, what's this? Looks like Pickle swallowed one of my Thundercats action figures. We better take him to the vet right away. Moby, you may have saved this cat's life. What? Okay, fine. I'm sorry for asking you not to perform diagnostic procedures on this cat. Let's go to the vet.
Okay. So hopefully it kind of gives you some practical understanding. And again, I'm not going to like test you like how does this work? Like what are the specifics? It's just so that you're aware what radiation and radioactivity can actually be used for, in our daily life. And it's not just like something that you would do in a lab, right? It's something that, has actual practical uses. So we're going to move on to part number 2. We're going to look at the type of nuclear reactions. So if it's a nuclear reaction, where is it taking place in an atom? In the nucleus. Very good. All right, so the nuclear reactions take place in the nucleus. What things are in the nucleus again? What 2 subatomic particles? Say it. Protons and neutrons. Good. All right, so the first nuclear reaction that we're going to be examining is nuclear fission. Fission. And this is the process of splitting a nucleus into two nuclei with smaller masses. So you're going from something big and you're going to split it into into something smaller. Okay? Fission. Fission sounds like the word division. Well, isn't that what happens in division? Don't you take something bigger and make it smaller? That's all division is. And so this one's pretty easy to remember. Fission sounds like division. And if you can remember that, then you can remember what's pretty much going on with nuclear fission. Typically, atoms above atomic number 90 can undergo fission. This is because their nucleus is large. Okay? And the energy that is released during this reaction can be used for electricity or nuclear weapons. Those are kind of the two main uses, I guess. So for nuclear energy or nuclear weaponry. Okay, so we're going to look at what's going on. We're going to look at chain reactions. This is one of your vocab words. A chain reaction is an ongoing series of fission reactions. So one little thing triggers a reaction and then it just keeps going and going and going and going and going until it either runs out of the material or it gets stopped. Okay, and so we'll talk about how that is. And this is exactly how nuclear power plants generate electricity. And we'll go over this as well. Because this is a very, we're still debating whether we should be using nuclear energy. The Bill Nye that we watched, right, talked about what do we do with the nuclear waste. If we had a solution to the nuclear waste, then I think that nuclear energy and nuclear power would probably be our future for sure. But until we can have a safe way of handling the nuclear waste, it's kind of debatable still. Like, should we be doing this? What are we going to do with the waste? And so, again, it hits into that kind of gray area of should we be doing this or should we not be doing this? Just because we can do something, should we? Okay. So a chain reaction is a main part of fission. And so if you think about playing dominoes, like the game, not like you're ordering it from DoorDash, but actually setting up the dominoes. Right? Has anybody ever played dominoes? I know I used to play with my grandpa. It's not a super popular game, but it is fun. Like I can't even remember how to play it. It's been so long. But I always enjoyed it. But you're setting up the dominoes like as kind of like setting off that reaction. And we're going to actually do a lab where you do this. So you have the line, you tip one, and it causes all of them to fall. Well, that's kind of what's going on in a chain reaction with nuclear fission. And so one domino triggers the whole thing to start. Okay, so nuclear fission occurs when a scientist bombards a large isotope with a single neutron. So you have this large isotope. Typically it's going to be unstable anyways because it's so large that strong force is not strong enough to keep the nucleus together. And so it takes one little thing and it's like, I'm out of here. Like the nucleus starts to decay and change, right? And typically it's just one little neutron that can cause this. And so this collision causes the larger isotope, the nucleus of it, to break apart into two or more smaller elements. And these reactions release a lot of energy. And the amount of energy can be calculated that's produced during one of these reactions using Einstein's famous equation, E equals mc squared, where E is the amount of energy that's produced if you take the mass and then times it by the speed of light squared, which is the c squared. Right? So, and we're going to look more at energy and calculate it later on this year, but it's calculated in joules. Mass is obviously kilograms, and then the speed of light is meters per second. So this is probably what Einstein is the most famous for, is developing this equation to determine the amount of energy. Okay, so here we're seeing a single neutron. Here is a nucleus. Typically, this is a uranium nucleus. And so the neutron hits into the uranium nucleus, and it causes the nucleus to split. You get two smaller nuclei. Because the neutrons are not destroyed, the protons are not destroyed, all that happens is like this hand of cards gets reshuffled, and now you have two hands instead of a single hand. Like if you think of the nucleus as like holding cards, okay? And so those cards don't get burned up or destroyed, they just split, and now you have two hands, or they're shuffled up. But the key here is that a bunch of energy is released, and 3 extra neutrons, okay? And so the uranium now is not uranium anymore because it has a different number of protons in the 2 new atoms that are created, and the energy, and then the 3 neutrons. So if you have 3 neutrons here and you have more uranium, what do you think can happen? If all you need is uranium and neutrons for these reactions to keep happening, what's going to happen if there's more uranium that's in the area and you have 3 new neutrons? Jack's like, right? It's going to keep going and going and going. It's going to go until you either run out of neutrons or you run out of uranium, whatever comes first. Okay? And so this is just showing it again. Uranium-235 is the unstable nucleus. The neutron hits it, and then it splits. When it has the uranium-236, because it's gained an extra neutron, that sends it over the edge. Like that's one too many, and the nucleus can't stay together. And so that's where you get the split, and then the release of those 3 neutrons. Okay. And again, this is just showing kind of the reaction. So this is showing a single fission reaction. Here's what it looks like more realistically. Here's the uranium. Here's the neutron. It hits. 3 energy gets released. You get, I believe it's krypton and barium. I need to look it up, but I'm pretty sure it forms krypton and barium. And then here's my uraniums, and there's 3 more neutrons that get released, and there's 3 uraniums there. So guess what? This reaction happens here, here, and here. And then this reaction, if there's more uranium, causes 3 more reactions. And this one causes 3 more, and this one causes 3 more. And it just kind of grows exponentially that way. So this is why it can get out of control very, very quickly and easily if there are neutrons and if there are uranium isotopes available. It's going to keep going. Nothing will stop it until those things are gone. And so it has to be maintained and controlled so it doesn't get out of control. So we're going to end today with this video.